My name is Ken Raffenetti. I am a software developer at Argonne National Laboratory, and I'm here to talk to you about interconnects, specifically in the context of HPC systems. So some background about myself. I am primarily an MPI person. I work on the MPI-CH software library that's maintained at Argonne National Laboratory and also extended by various vendor and academia groups to deploy on large-scale supercomputers. So I bring a lot of like MPI focus to interconnects when I talk about them, so just keep that in mind. But feel free to ask questions or whatnot throughout the presentation. This is going to be a little bit high level in terms of this track, where I'm going to talk a lot about the things that interconnects can do, but less about the actual nitty-gritty performance details. There's a reason for that. It's because I maintain an open source MPI, and I don't want to make any of my vendor partners upset. I want to make sure to support all interconnects in MPICH, and not just the ones that perform the fastest currently. So just to start out, this is a slide that this is a table that comes from the DOE Exascale report that I think is about 10 years old now. This was just kind of some projections on system architecture going forward, and the timescales here are a little modified because I think things ended up taking a little bit longer than originally anticipated. But what I have here at the thing to focus on here is interconnect bandwidth. This is pretty much on trend. If you look at the systems today, like I think we had a presentation about Summit at OLCF, where they have dual rail 100 gigabit interconnect at the node level. So that roughly fits with that 20 gigabit per second off node bandwidth. And then in the exascale machines, the projection was 200 gigabits per second off the node. We'll see if we get that, but things are still kind of increasing pretty rapidly in terms of node bandwidth, node interconnect bandwidth. So this, again, I'm going to focus on kind of trends in interconnects, and this is kind of like an easy one to start with, is bandwidth off the node. But in terms of general trends in system architecture from that table, in terms of, bandwidth is increasing, great. What else is happening, and how does the interconnect fit in with that? So we're seeing nodes increasing on large-scale HPC systems, but not in a really rapid pace. We're seeing, thousands of nodes, maybe up to tens of thousands of nodes. That's not, things aren't going crazy in terms of node count, but things are kind of rapidly increasing within the node, the number of cores and threads. So now we're seeing CPUs with 64 physical cores. We've got accelerators with lots more cores that can handle computation. The cores themselves aren't going up in speed necessarily. The frequency is staying pretty much stagnant. So what does this mean for networks? Sure, we have more cores driving the network at the node level. And because we have more cores, we're sharing more infrastructure. The network infrastructure is being accessed by lots and lots of different cores on the node. The aggregate communication from each node will increase moderately. But if you're thinking about many MPI processes running on the node, yes, you're having more and more messages generated from all these MPI processes. But instead of doing these big block communications from a single MPI process, it's probably going to be chopped up into smaller messages. And another thing to be aware of is that a single core today may not be able to fully saturate the NIC. In fact, it almost certainly won't be able to fully saturate the network card. So you're going to have, you're going to need to run more and more processes on the node just to fulfill that bandwidth that's available to you. Okay, so architecture-wise, I think in the abstract of the talk, one of the goals was to kind of talk about bottlenecks in the network interconnect architecture. And so to talk about bottlenecks, I think we want to back up and look at network infrastructure from past systems, which is kind of what this diagram is looking at is this is kind of like a very simplified, pass system where you had your processors, you had some memory. There's kind of I think in the past it was this Northbridge chip that kind of handled interactions between those two, and also interactions with the I/O bus, which is where the network adapter was hung off of, and then the traffic would go out to the network switch. So there was a lot of different disaggregated pieces here. There was a lot of software in between handling the interactions between all these components, and in order for you to achieve any kind of good performance out of a kind of a loosely coupled system like this, you needed to have a very balanced approach to your software. And yes, so there's bottlenecks all over the place. There's bottlenecks in the processing layer and the I/O interface, and also at the network end host, fabric itself. So this is, again, this is kind of a simplified background of what we're going to talk about. So the three main topics I'm going to cover are network adapters, network topologies, and also network interactions with processor and memory. And we'll kind of show how some of these bottlenecks in the past architectures have been addressed and how things work today. So traditional network adapter bottlenecks. If you think about network communications, say in the time frames listed here at the bottom, and maybe in the 80s and 90s, the network was there, and what was it there for? Maybe we're going to use your computer network to talk to a printer, or maybe grab a rudimentary website or something. But this wasn't really, HPC wasn't necessarily, at the forefront in this time period. So network speeds in the early days, they kind of plateaued around one gigabit per second. The features provided were pretty limited, and if you were trying to build a large-scale system, you weren't just going to buy something off the shelf. That wasn't really going to work for you. Things might not scale, or you might not get the performance you expect or you desired. So what happened? So HPC systems, HPC vendors started to design more specialized hardware for high-performance machines. And so the two main things you see in HPC networks is high bandwidth and low latency. That's what the HPC systems kind of focus on. So examples of that today are things like Mellanox InfiniBand, where an EDR InfiniBand card gives you 100 gigabits per second per link on an interface. And as I said, the bandwidth is still increasing, quite at a pretty good pace. HDR systems, I think, are starting to show up now. If you think about, or if you've read about the Frontera machine at TAC, it's deploying HDR InfiniBand, which is 200 gigabits per link. Though I think in that case, they're still using 100 gigabit at the node link, and then 200 gigabit between switches. Multiple network links are becoming more common in HPC systems. So we saw, like I mentioned, Summit and Sierra machines both utilize what they call dual rail. So you have multiple network links at the node level. And other machines like the Japanese Post T2K similarly. And these multiple network links can be used, though not necessarily, can be used to create more interesting multi-dimensional or Torah-style networks where your interconnections with the other hosts in the system are maybe not quite as straightforward as they would be in a fat tree topology that's maybe more commonplace, or at least in the past might have been more commonplace. And so what I'll say this, and I think this is still mostly true, is that the peak network bandwidth is not a major limitation of system builds today. It may be expensive to get lots and lots of aggregate node bandwidth, but it is possible. And so I would say that's not really a major limitation of system builds. Latency, though, is, again, the other big benefit of HPC interconnects is low latency. Latency can be an issue. There's been a lot of work in MPI libraries and in the lower level network APIs to really get the best latency possible. But we're starting to run into limits that are more physical than they are software or hardware. We're talking about just the light going across wires or energy going through the copper wires. There's a point where we can't go any faster. We're running into a speed limit. So there's some room to improve. We'll keep making our software more efficient and whatnot. But yeah, that latency may start to be more and more of an issue going forward, I guess is the point here. And so one thing I think you are seeing in system designs today is a much more dense configuration. Nodes are quite dense. Systems themselves have a smaller footprint. Therefore, your latencies might shrink a little bit because of that. That you're not going these great distances over fiber optic cables or whatnot. So bandwidth and latency are big benefits of HPC networks. There's other things to consider, and I think I'll touch on those in later slides. But things like message rate, or maybe more importantly, what I would refer to as injection bandwidth off the node. So, it's one thing to have low latency. It's another thing to have a high message rate. So if you check out some of the network benchmark suites available, like Intel Micro Benchmarks or OSU Micro Benchmarks, one of the common network benchmarks is message rate. How many messages can you send between a pair of processes or some number of processes, and so obviously higher is better in this case. But with the high level of node concurrency, just being able to send a high number of messages is one thing. But actually, at some point we're limited by how many messages the network interface card itself can accept. Like how many distinct separate messages it's able to inject into the network. And so that's something that's becoming a little more. We're spending a little more time trying to understand how that affects applications currently. Also, network congestion. So I talked about a little more complicated network topologies, and obviously with that comes interesting characteristics. When the network is under heavy load, there can be congestion that affects your application. Not just because of what your application is doing, but what the applications around you are doing. And so there's a lot of research and new technology coming out today to address that issue as well. All right, so this was again our simplified architecture diagram. How things have changed over time. So this is a kind of a more current diagram of how things look. So now you see the processors themselves have a memory controller kind of integrated onto the die. And so now we get better memory bandwidth because of this tighter integration. This also helps the network communication. So data transfer data transfers using the network are now better coordinated with the caches that are on the CPU. And then, but we still have this I/O bus. Our network communication is still going through this I/O bus to reach the network adapter. There's several technologies here. There's PCI Express. There's Hypertransport. I think Infinity Fabric was the other one we heard about today. Maybe NVLink is another. I guess the takeaway here is that the I/O bus, not necessarily a bottleneck. It still does add some latency into the system, but in general, the bandwidth provided by the I/O bus is not going to limit you accessing what the network adapter is capable of. At least that's the hope. This slide, this has been in the presentation for a couple of years now, and I added a question mark because I'm starting to think that this probably won't happen. But one thing we thought we might see in future systems was, again, the network adapter here is hung off the I/O bus, and that's kind of adding a little latency into the system. We thought we might see the network interface actually get integrated into the processor die as well. And the benefits here were, what you would probably think, maybe lower latency. Now the control messages between these devices, the memory controller, the network, and the processor are all within the chip. But we haven't really seen this hasn't really emerged in a viable product so far. So I guess it's just unclear if the benefits here are actually worth it, or the latencies are so dominated by what's happening off the node that this tighter integration on the node is not necessarily worth it. And I think there's a lot of effort here. There's a lot of actual hardware engineering that would have to go into making all these things play nicely together. I mean, it might eventually happen. It just hasn't happened in the time frame we were originally thinking of. Okay, so that's that kind of deals with the network interface cards and how they communicate with the processor and memory. The next thing I'll talk about is a little bit about processing bottlenecks in traditional protocols. So again, I'm going to talk a lot about Ethernet or Internet IP protocols in comparison, in contrast with HPC systems. It's not that Ethernet is necessarily bad, or in fact, Ethernet actually can work on HPC systems. It can work quite well on HPC systems, but I'm talking about it more in a traditional sense, like what the Ethernet from like your laptop or your desktop. And so in an Ethernet system, for example, you have TCP and IP, or TCP and UDP protocols. These are really generic protocols that are designed for general purpose networks. In the case of these protocols, the host processor is doing most of the work here. There's data buffering happening on the host. There's data integrity checks happening on the host. There's some aspects of the IP protocol are all happening within the OS's TCP/IP stack. And this is a multi-layered protocol where there's signaling happening up and down between the layers. And so again, this is all kind of general purpose and works quite well, but there's, it's software heavy and therefore has lots of overhead. Ooh. So what has HPC done to kind of offset the overheads of these more traditional protocols? So we call this kind of the offload era. So modern networks spend more and more real estate on the network chips, on offloading some of these things that were traditionally done in software in traditional protocols. And so what types of things can they offload? Things like reliability, the packetization of a message, or a network transmission. That can all happen at the hardware level rather than in software. And then also, HPC networks take great efforts to bypass the operating system entirely if possible. So I'll cover it later, but we'll talk a little bit about registering memory with the operating system, but then doing your data transmission from user space, which is one of the bigger savings of HPC interconnects. Okay, so this is just some pictures on trying to compare the network stacks of say, a traditional Ethernet versus an HPC offload, kind of offloaded network. And so, what you might know from an Ethernet network is the sockets interface, and that sockets interface uses TCP or UDP underneath. And that's a pretty high-level interface, right? You kind of write data in and read data out, and it kind of works. It works mostly synchronously, and then you can build all types of technologies on top of this: file systems, web servers. MPI can work on top of sockets, but the point is, it's very general purpose. In a hardware offload scenario, much of the, what's highlighted in the orange box, much of this is done in hardware, if not all of it. And what's exposed by the hardware is a very low-level interface. Not like sockets at all, but in the case of, say, InfiniBand, you have this verbs interface. And I don't know if anyone has ever seen a Hello World program in InfiniBand verbs, but it's, I think a short example may be about 1,000 lines of sending a message between two processes. It's a pain to program, but you do get really good performance overall. And I wouldn't expect folks in this room to be using those, using that interface directly. It's things like MPI or PGAS are built on top of that low-level interface that's exposed by HPC interconnects to give programmers a little bit more productivity. So I mentioned InfiniBand verbs. That's one example, but that's not the only example of network vendor-specific APIs. There's also Intel's PSM2 performance scaled messaging interface. This is for Intel OmniPath architecture. IBM PAMI, though that may be on its way out these days. Cray has the Gemini and DMAP interfaces for their Aries interconnect. So the point here being that there's lots of different, network vendors. There's lots of different APIs. What does that mean for people who want to use them? Well, there has been an effort recently to kind of consolidate those APIs, standardize on a more common interface. Though I could probably use the XKCD cartoon to talk about standards and coming up with a new standard. So the result is we have kind of three competing standards right now. We'll see who wins out in the end. The first being the Open Fabrics Interface, or OFI, aka libfabric. This is an effort, out of the Open Fabrics Alliance group, which is very involved with InfiniBand specification and also the software tools around using InfiniBand. This is more broad than InfiniBand, though. So, main contributors to this are Intel, Cisco, and others. The OFI library exposes a low-level communication API. It has both message and remote memory features. And then underneath that API, there are various providers, and those providers are typically maintained by network vendors, so that you can, if you code your application to the OFI interface, then hopefully the network vendor you're working with is supplying a provider that will perform well on your hardware. In contrast to that, there's the Unified Communication X effort. This is something that's driven by a somewhat different group of vendors, mainly Mellanox in this case, but also IBM and Oak Ridge contribute largely to this, ARM as well. And so again, the goal here is very similar. And a lot of these things, again, they provide message APIs and remote memory access. Myself, we use these heavily inside the MPI library because this is where you can go to get some of the best performing, some of the best network performance for, say, Mellanox InfiniBand or Intel OmniPath. Like I said, the vendors themselves are contributing the code to these libraries, and then for us as MPI people, it's great to just plug that in, and that means MPI is going to work well on the systems that utilize that hardware. And a third example here is the Portals 4 network API from Sandia. Portals 4 is a little bit different, as it's less of a software API as it is a hardware API. Portals 4 is kind of a thing that Sandia publishes to say, here's what I need out of my hardware in order for my applications to work well. And I think that this eventually, this is more of a reference document for hardware vendors to understand what the hardware should do well in order for them to sell the network to centers like Sandia who want to buy machines with good interconnects. All right, so that covers the state of APIs. So I touched on it earlier. how are we going to achieve bypassing the operating system, which traditionally has handled the TCP/IP stack? That's a heavy, thick software layer, and so the goal is how can we bypass that? How can we do network? How can we interact with the network from user space? Well, we still have to do a little bit with the operating system. Because the operating system is managing the memory, right? It's handling the virtual memory system, and so say I want to communicate out of a buffer that I've allocated in my process. Well, I need to tell the operating system I'm going to be communicating out of this buffer. Therefore, it's going to lock those pages into physical memory so that when the network goes to access them, they'll be there. The right data is there for it to access. So how does memory registration work? So a process is going to has some virtual address, a buffer sitting at some virtual address and a length, and it says I want to register this. So it sends a request down to the OS. The OS handles the virtual to physical mapping, as I said, and it pins that region into physical memory on the host. Just a note here that process is not going to be able to map memory that it does not privately own for security purposes. So the OS is going to take care of that security function in this case. The network adapter at this state during a memory registration is going to cache this virtual to physical mapping and issue back a handle to say, all right, I know where this memory is currently located. Use this handle again if you're going to be communicating in and out of it. Handle is returned up to the application. Great. And so now, from user space, once this memory address is registered, in contrast with a traditional network API where, again, you do a write into a socket, for instance, and the OS is going to buffer that information and then send it out onto the network, the process is going to be able to tell the network to issue a communication directly, and it won't have to interact again with the kernel. It eliminates this heavyweight context switch between user space and kernel space. And also, these memory registrations ideally are being cached so that if you're using the same buffer or the same buffers over the course of your application, the next time you go to register that buffer, it's going to detect that it's already, the registration is still cached, and it won't have to go through this heavyweight process again, because this is expensive. And I think there was a question earlier about, in the context of GPUs, when exactly, it's better to go, through the host than through GPU direct RDMA. A lot of that has to do with the cost of registering buffers, particularly on GPU. I think that registration can be quite costly. So this is expensive. This part is if your buffers are already pre-registered, then your communication cost is actually quite low. Because again, you're not going through the OS, and you're not actually involving the CPU at all, other than filling out this, what they call in InfiniBand, a work request for the network adapter to issue some communication. So these are some diagrams of how this kind of looks. Again, this is simplified, but say for instance, in a send-receive communication in an MPI context, how this would look. So your processor is going to fill out a receive request. In this case, it's going to enqueue that into some network queue and say, here's who I'm going to receive data, or here's who I'm expecting to receive data from, and here's where I'd like it to be placed. Here's the memory address I would like it to be placed. On the send side, similarly, here's the message. Here's who I want to send it to. Here's the memory where you can go find the data. And then at this point, the network interface gets a hold of this request. It reads directly out of the memory segments without having to go back to the processor, and it will send it across the network to the target. On the target side, it's matching. It's matching the message information with the incoming data and placing the data directly into memory, again, without involvement of the CPU. And then it enqueues there on the right side, the red boxes are kind of completion queues where then the processor can pull to see when that message that it issued has actually been completed. In this case, we have a hardware ACK going back to the send side, and similarly a completion on the send side saying, okay, that send message you told me to issue has now been completed. Similarly, this is, if you're familiar with one-sided communication in MPI, this is you can imagine this as like the previous diagram, but in this case, the receive side isn't involved at all in the communication. So you have the send entry contains information about the send buffer and the receive buffer in this case. And so once that gets issued down to the network will get the data out of the memory segments on the local host and put it directly into memory on the target host. And you see here the send side gets a completion object, but not the receive side in this case. Similarly, atomic operations are supported in a lot of HPC interconnect hardware. So this looks a lot like a RMA operation, except that there's, what might happen is they fetch a memory address out of the target host's memory segment, perform some computation on it within the network hardware itself, and then store the result in the target memory segment, or perhaps if you're doing, say, a fetch and op, you're fetching some memory location back to the origin host, and again getting a completion object. So what I've kind of covered here is, in terms of the network protocol stack, these are highly specialized. Your HPC systems are obviously highly specialized network stacks. The complete opposite end of the spectrum of your TCP/IP or UDP, where you can build all types of different technologies over them. These are pretty much purpose-built, specialized for MPI or PGAS or that type of programming model. And so this focus continues today. It's going to keep showing up and keep getting more and more specialized. I think some of the areas of focus you'll see are non-contiguous data movement, multiple contexts for multi-threaded architectures. So as I mentioned, we got more and more cores on the node, and you may not be running, say, flat MPI across all the CPU cores. So to efficiently utilize the network, you might want to run multiple threads. Those threads need some level of hardware independence to operate efficiently. So that's where the multiple contexts come into play. Offloading the actual features of MPI and PGAS onto hardware. This exists today, and it's going to keep getting more and more specialized. So put and get. We're kind of the first ones. You've got hardware RDMA support to do things like MPI put and MPI get. Atomic operations more and more are being supported in hardware, as I mentioned. MPI collective operations is an area where things are starting to emerge in the hardware. So Mellanox has a library called Sharp, where you can actually perform a large part of the MPI collective operation is offloaded to the hardware, even the reductions themselves. So where you're doing, I think maybe a marketing term, but the marketing term is in-network processing. So you're actually, doing partial reductions, say at the NIC level or the switch level, and therefore it minimizes the amount of communication being done. Because it's able to kind of do these intermediate steps in the different hardware layers, and also tag matching. So MPI message tags traditionally had been done. Message tag matching had been done in software. That's part of the MPI library's job. We're starting to see more and more tag matching done, or tag matching. Being done possibly in hardware. Cray C-Star this is an older interconnect, but it had an implementation of hardware tag matching. The Bull interconnect, which I think you see in machines in Europe more commonly, has tag matching support in hardware. And also Mellanox InfiniBand actually has this. I don't know if it's what the status is. I think last year it was still in beta. But if you had ConnectX-5 network adapters or later, you could actually load a firmware that supported hardware tag matching as well. All right, that kind of covers network adapters up until this point. Maybe it's a good time to stop for questions if people have any. Otherwise, I'll keep going. Question?
So you mentioned like in InfiniBand a bunch. It seems like within a data center, a lot of the cloud providers are switching over to that same sort of network. So does that mean the gap between the two is closing, or like what's your comment on that?
That's a good question. I don't work with data centers, that the non-HPC centers enough to say for sure. And again, InfiniBand also has this IP over IB capability where it can provide an internet protocol layer on top of the InfiniBand hardware itself. But I guess what I would say is that one of my hobbies is reading the Linux RDMA kernel mailing list, and it's the email traffic relating to development of the RDMA subsystem within the Linux kernel, and it's a really active subsystem of the Linux kernel. There's a lot of vendors contributing a lot of code to support different use cases, whether that be NFS over RDMA, accessing non-volatile memory technologies over RDMA. So yes, I would say that there's more and more use cases that work well that I could imagine are being deployed in data centers. Conversely to that, though, kind of all the other InfiniBand competitors have gone away recently. So Intel's OmniPath architecture, they don't call it InfiniBand anymore. They have an InfiniBand compatibility layer, but it's its own thing at this point. Cray just recently introduced a new interconnect that's different from InfiniBand. So yeah, I think that I would say InfiniBand and RDMA are two separate things, and I think there's two different things happening. RDMA technology is getting more mature and is working well for more use cases, and I think that RDMA, different interconnects are also able to support RDMA capabilities in a performant way, and it's not just InfiniBand anymore. InfiniBand is probably still going to be the best performing one. It's still the one that shows up on the most HPC systems in the top 500, but things like RDMA over converged Ethernet, Rocky, that's becoming more and more mature as well, and you might start seeing that on systems too. Question?
So to get the benefit of RDMA and InfiniBand, will using MPitch sufficient, or some specialized MPI implementations are required?
So yeah, this is a difficult question to answer. So what we have support for in MPitch are essentially those network APIs I showed, the OFI and the UCX, and not so much Portals 4 these days. And so those libraries perform very well. Now, what MPitch derivatives give above and beyond MPitch is that they may be tuned for specific use cases, or more importantly, probably is specific node architectures. So something like an Intel MPI, which is based on the MPI-CH library, has better support for Intel shared memory technologies, like optimized for the microarchitecture. But in terms of node-to-node performance, what you get in MPitch is going to be pretty close to what you can get in an optimized MPI library. Other things that may differentiate is the way they handle multiple network links, or say the multi-threaded strategy for applications that use MPI thread multiple. These things can all differ based on, again, the targets of those library deployments, and also just the priorities of the vendor. But MPitch, OpenMPI, similarly, you're going to get pretty good performance out of the box. But in general, if you're running on an HPC system, use the one that's supported by the center, because it may have some optimizations built in, or more importantly, you're able to get support probably better than you would just emailing the MPitch list saying, I'm trying to run on Summit, what's going on? That's going to take a while for us to answer. All right. Let me see if I'll go through I think the last few things here are not quite as dense. So we'll talk a little bit about topologies, and just kind of as a thought experiment, or just conceptually to start from a good point, how your machines are interconnected with each other matters in terms of performance. So coming from an ideal connection topology, which you would consider a crossbar in this case, this is essentially an all-to-all, where you have distinct wires going from every core in your system to every other core, or every node in your system to every other node. A crossbar is not really scalable, right? Currently, you can go up to about 64 ports. This is probably what you would see within a switch, for instance, but it's too expensive to scale any higher than that. But the point here is that you have distinct paths to every other port in your system. Therefore, none of your communication will block on any other communication. But again, that's not really realistic in today's HPC systems. What is more realistic is a fat tree topology, which is kind of pseudo non-blocking. And so these you see pretty commonly. What the characteristics of a fat tree are that between all pairs of processes there exists a non-blocking path, but not all paths are non-blocking. And so what you see is that as you go up in the layers of your network topology, the aggregate bandwidth stays the same between all of the layers. That way there's always this non-blocking path from one place to another. But again, fat trees can get pretty expensive, though if your node count is low, then it's pretty realistic to see these deployed in production. Some of the other topology trends, in the name of scalability, you see things like torus topologies or dragonflies. And the reason for this is that you get a linear increase in the number of links and routers needed to support the system. But the drawback being that any communication might have more than one hop, or will likely have will have multiple hops, and that congestion is possible. The takeaway from these kind of emerging trends is that topological locality is important, and it's something that's not going to get any better for you. You're going to have to really, really pay attention to how your data is laid out on these systems. These are just some examples of how congestion can impact communication performance, or in this case, the number of hops between targets. This is, again, the takeaway here is how you lay out your processes within the topology will matter quite a bit. And so this is maybe you have a three-dimensional structure in your application, and then if your processes aren't laid out closely together, then you're going to see weird performance implications at runtime because of the extra hops between neighbor communication, things like that. And again, these are performance numbers. It's not critically important to understand here, but I think I heard earlier in a presentation something along the lines of flops are free, data movement is expensive, and yes, that's really important, especially when you're getting to the network layer. And just some quick notes about network interactions with the memory system and with cache. So the diagrams I showed, the network interface, basically reading and writing directly from the memory segments in your system. And today, modern systems, these network interfaces are smart enough to interact with the cache coherence protocols within the node. It's the case that users don't have to know when data is in cache versus in memory in order to do communication. That's all handled cleanly underneath the covers. And in fact, we don't even have to do that in MPI. The network libraries below us handle that for us as well. So again, these are pictures, and this is the old architecture with the North Bridge still in the diagram. But here, the point being, if your application buffer is in cache and you're going to send it, then the NIC will know to flush that cache data into memory when doing the communication, and conversely, there's similar support on the receive side. One note about cache injection. So this is something I spent some time looking around to see, there was research going on in this topic maybe 10 years ago or so, maybe more, whether or not there was a benefit to directly injecting data from the network into cache. I don't know if this is actually being investigated anymore, because I think there's probably, it's probably a little too, it's probably a little too complicated to foist onto application developers. Because I mean, ultimately, what can happen is you're polluting the cache with incoming data, whether or not the CPU is ready to handle it, and that can be quite disruptive to your compute performance. Atomic operations as well. So one of the things about network interfaces that can perform atomic operations is that they're only atomic with other network atomic operations. They're not atomic with CPU operations, and so that's problematic if you're trying to do both at the same time. MPI can potentially help you here, where we will only do atomic operations with one or the other, but not both. But again, if the user does something, if the user's using non-MPI atomics, then that will complicate things. So again, I talked about this earlier, and it's something that I'm not sure will happen in the next 5 years or so. But one potential benefit of that network processor integration was that it would solve this problem of conflicting atomic operations. I don't know if that's something that's going to happen soon, but that would be nice. It would simplify things quite a bit. A note on network interactions with accelerators. So PCI Express itself supports peer-to-peer data transfers. And so, for instance, with things like GPU Direct RDMA, you can read and write directly to GPU memory from a network interface. So that coordination exists today, and you can avoid copying data to and from buffers on the host. Like I said, GPU Direct RDMA is one example. There's others like AMD's ROCm, and again, this is a very active area within the Linux kernel community, because a general purpose solution is not yet available, from what I understand. GPU Direct RDMA is actually a non-standard kernel module you have to load onto your system. So if you're, on machines like Summit, where the system administrators are knowledgeable of that, it should be loaded and available to you. But if your system administrator is not familiar or is worried about the security implications of something like that, it might not be available to you. So a general purpose solution is probably coming, but not yet available. And so that's about all I have. Just as a quick summary, so interconnect technologies are still advancing. It's pretty interesting, some of the things that are now happening in the hardware offload space, especially with collectives, I think. Hardware integration is helping to remove the bottlenecks that I showed in those diagrams early on in the presentation. And we hope to see this progress in the future, though again, as I touched on, I'm not sure network integration is coming quite yet, but hopefully someday. But just a couple of takeaways, the network topologies and high core counts, your network resources are becoming increasingly shared, and therefore you have to be aware of that in order to fully to efficiently take advantage of them. So that's about all I've got.